Welcome to Lab 6, Magnetic Molasses. We're going to go through our intro, visual model, procedure, observed results, computational model, computational results, and discussion. So for our intro, we wanted to collect the observational data of a magnet falling through a conductive tube of aluminum foil, as well as model this interaction computationally and compare our computational and observed results. So we found that the average time for the magnet to fall was 1.05 seconds. In this lab, we used Faraday's law, and this equates the dot product between an induced electric field and the length of the outer edge of a closed area to the negative derivative of the magnetic flux. And we know that the magnetic flux is the dot product between the magnetic field and the area that the field passes through. In this experiment, the first equation is used to find the change in flux. And we know that the electric field resulting from the change in magnetic flux is in the same direction as the current. The magnetic force on a wire loop is essentially the cross product between the current times the L vector and the magnetic field, where the magnitude of L is the length of the wire. And the following equation is derived when considering a magnetic force on a loop. We also use Newton's third law, in that the magnetic force on the loop is equal in magnitude and opposite in direction to the force on the magnet by the loop, as well as Ohm's law, where current is equal to the potential difference divided by resistance, and the induced EMF is the potential difference in this experiment, and that's equal to the change in magnetic flux. In our visual model, we have our magnet as the system, our surroundings being the tube of aluminum foil and earth, where F1 represents the force from the magnet on the loop, while F2 represents the force on the magnet by the loop. For our procedure, we marked the north pole of the magnet. We measured various properties of the magnet as well as our tube, and then we dropped the magnet through the tube while recording. The interaction was computationally modeled using VPython. The average time was found to be 1.05 seconds, and we have also listed several other measurements. For our computational models, first we have the initial conditions and constants for the model. This includes the properties of the tube and magnet that was listed previously. And we note that the initial velocity is 0 because we began at rest. For the magnetic field and magnetic flux, general formulas are used. For our simulation loop, we are calculating the force on the magnet by the loop and the force due to gravity to find the net force of the magnet. The loop also updates velocity and position of the magnet. These are the results of our computational model, with the dipole moment from lab 3 on the left and the dipole moment that was found using trial and error on the right. So when the value of the magnetic dipole moment from lab 3 was used, the computational model predicted that the magnet would not exit the tube, which was not observed. And when the magnetic dipole moment was decreased to 4.927 amp time meter squared, the computational model predicted that the magnet would take 1.05 seconds to pass through the tube, and this is the same time as the observed average. So our results suggest that the value for the magnetic dipole found in lab 3 is inaccurate, and that 4.927 may more accurately represent the true value of the magnetic dipole. Possible sources of error include contact and/or friction, air resistance, timing inconsistencies when determining the point at which the magnet enters and exits, as well as measurement errors. If the resistivity of the conductor was reduced to be close to 0, the amount of time that the magnet takes to fall through the loop would increase because of the force on the magnet from the loop would be larger than the original value. If holes or slots were cut into the tube, it would take less time for the magnet to fall through the tube because the magnitude of the force on the magnet would be less than the original magnitude.